Alrighty, welcome to DC Motors Part 2. In this video we're going to talk about electrical characteristics of DC motors. And this video is very, very important, right? And some prerequisites is that you should have watched the video on resistance and DC motors Part 1. This will give you good background information for this video. And again, some of the stuff I'm going to cover can be a little complicated. So please let me know if you have any questions. I'll be happy to answer them. Alright. So let's get into it. So some vocab before we get into the meat of the stuff is something called the electromotive force, or EMF, right? So EMF is very, very similar to potential difference, right? There's only one slight difference. Just to review potential difference. Potential difference is how many joules of energy is transferred per coulomb of electricity, right? And the term potential difference is used when energy is transferred from electricity. For example, when you have lights, we have a potential difference because electricity is being transferred from electrical energy to radiation. In resistors, it's electrical energy to heat. In speakers, it's electrical energy to vibrations in the air or sound, right? And in motors, we're converting electrical energy into rotation and motion. Okay? So the only difference between potential difference and EMF is that instead of transferring energy, instead of energy being transferred from electricity, energy is being transferred into electricity, right? So we're generating electricity from something else, right? And this something else can be batteries, right? Batteries are of course a source of a source of EMF, right? And the fun thing is that motors are also a source of back EMF or EMF, right? So if you think about it, and if you're say study dams or like wind turbines, right? In wind turbines, they have a magnet rotating around an electromagnet, right? Very similar to a motor, right? And this rotation generates electricity, and it's what we use in our houses, right? And so when you power a motor, because you created a permanent magnet spinning around an electromagnet, when you power a motor, it also generates power back, right? And we call this voltage returning from the motor back EMF, okay? And the magnitude of this back EMF, this is very important, the magnitude of the back EMF is directly proportional to the motor's rotational speed. So the faster the motor is rotating, the more back EMF is produced. If the motor is not rotating at all, zero back EMF is produced, okay? So that's the electromotive force and back EMF. Okay, so here I have the electrical breakdown of motors, and all the diagrams you see I kind of hand drew on a whiteboard. So sorry if it's a little messy. Let me know if you can't read anything. I'll be happy to clarify. But this is kind of an electrical breakdown of what the electrically significant parts of a motor are. Okay, and I use these circuit symbols. So I'm gonna kind of decipher what this means. Okay. So first we have our Vs, which is our supply voltage. And you can think of these two circles as the two terminals of our motor. Okay. The next thing here we come across here is this kind of squiggly line, which represents an inductor. And we haven't really talked about inductors in these series, so I'm going to briefly give a description. Inductors are these electrical components. They're basically just spools of wire. And the nature of these spools of wire is that it will temporarily store energy in a magnetic field, right? And say when the voltage supply is cut, the magnetic field will collapse and produce a voltage for a short period of time. And the more kind of spooled wire you have, the larger the inductance in that wire. Okay, so that's our inductor. And in motors, because we have a lot of spooled wire, because of all the electromagnets inside, motors have a very, very large inductance. Something to think about. Okay. The next component is this kind of jagged line right here that represents the internal resistance of a motor. And if you're kind of confused with what that means, I highly recommend you watch our video on resistance. And finally, we have the supply voltage or voltage EMF, the voltage coming out of our motor, right? And this plus and minus in a circle represents a voltage source. And so because of the motor is generating this voltage back EMF, right? I represented it as a voltage source with denoted by V sub EMF. Okay, so that's the electrical breakdown. And again, if you haven't watched our video on resistance, I highly recommend you do, because I'm about to use Ohm's law, right? So remember, Ohm's law was that resistance is voltage over current. And so I kind of rearranged the equation, and instead of just using voltage, I used it as I replaced voltage with net voltage. Net voltage in this case would be V sub S minus V of EMF, right? And so our current in our motor, our I sub M, the current draw of the motor, is equal to V sub S, voltage, supply voltage, minus V sub EMF, which is the EMF of the EMF generated by the motor, back EMF generated by the motor, divided by the internal resistance of the motor. So this is how you calculate current draw. And when you write software and you're trying to budget current to different motor systems, this becomes very useful. Okay. So now we know that what back EMF is and the general electrical breakdown of motors. We can talk about current draw and how and what it looks like during different parts of a motor's operation. Okay. So here I have another kind of whiteboard drawing, and this is supposed to kind of display voltage over time. And this dotted blue line here is the supply voltage, which is kind of steady, and this red line here is the back EMF produced by the motor. Okay, and I have kind of four different periods. One is the ramp up, so we're going to start the motor up at 0, and we're going to ramp it up, right? And we're going to talk about what the current draw in this ramp up looks like. The next part is free spin, where the motor is spinning very fast and the voltage EMF is very close to the supply voltage. The next part is load, right? So we're going to add some load to the motor, and because it's not spinning as fast with the load, the voltage EMF is going to drop. And finally, we have too much load, where we have so much load that the motor stops and we have 0 voltage EMF, and we're going to look at what the effect of that is. So first with the ramp up. Right? So ramp up, we're going to have something called a large current draw, right? So if you look at our equation, because in the ramp up our voltage EMF is going to start at 0, our current draw is also going to be pretty big as a result, right? And we call this large current draw in our ramp up inrush current, okay? And it can be pretty high with our FRC motors. All right, so that's ramp up. The next part is free spin. In free spin, our voltage EMF is very close to our supply voltage, and because they're close together, V of S is really close to V of EMF. And so the numerator kind of goes to 0, close to 0, and that makes our current draw pretty minimal. So when free spinning, our current draw on the motor is pretty small. Next, we're going to talk about load, right? So load is we're going to slow down our motor a little bit, and our voltage EMF is going to drop proportionally. And with load, current draw is going to increase as a result, right? Because V of EMF is dropping. And the fun thing with increased current draw is because the motor is drawing more current, the electromagnets produce a stronger magnetic field, right? And because of the stronger magnetic field, it's able to produce more torque. So the more load applied to a motor, the more torque it produces as a result. So something to consider. And then finally, we have too much load, where we kind of stop the motor with the amount of load we're putting on it. And in the situation with too much load, right, we have 0 voltage EMF because the motor's not even spinning, and this can be pretty bad, right? Because V of EMF is going to 0, we have a really big current draw, and motors usually can't handle a large current draw for an extended period of time, so the motor will burn out, and you have a whole mob of really mad build people. You don't want that. All right, now I'm going to talk about stopping a motor. Right? So what goes into that? What does that look like electrically? And so remember when I looked at our electrical breakdown, the motor has a large inductor, and when you cut off supply to an inductor, it releases the energy that was once stored in the magnetic field it produced, right? In the case of a motor, because the inductor is so large, right, the collapsing magnetic field creates a huge negative electrical voltage, and this negative electrical voltage can be so large that it can lead to arcs, and at least in brushed motors, it can lead to arcs between the commutator and the brushes of the motor. And if you don't know what that is, please watch part 1 of the DC motor series. Okay. So just to demonstrate that, I have my household drill, right? And this is a brushed motor drill, and we have these little vent holes here. So I'm gonna ramp this up to full velocity and quickly let go, and you're gonna see the arcs physically. You're gonna actually see the arcs inside the vent hole. So I'm gonna turn off my light here. I'm gonna ramp it up, and if you see that, you can see like the blue flash, which is the arcs of electricity jumping between the commutator and the brushes. And you might be able to see this also with the drills we have at Robotics. I haven't really given, so you can look for that. Okay. And so something to also consider when we're stopping a motor, we also have back EMF still present, right? So if we allow our motor to coast, right, because the motor is still rotating, right, still generating the back EMF. And so say we want to stop a motor immediately, the way we do this is by shorting the 2 terminals of the motor, right? And this basically sucks out the back EMF immediately, and the motor stops in an instant, right? So when we in software, we're talking about something called coast mode or brake mode. In coast mode, we let the back EMF kind of settle down by itself, and in brake mode, we are shorting the 2 terminals so that the back EMF produced goes directly back into the motor, and the motor stops immediately. Okay, so we talked about stopping motor. We talked about the electrical breakdown. We talked about some just characteristics during operation. So let's look over some problems and solutions. So one of the problems were if there was too much load, if there's too much load on the motor, right? And the only reason you have too much load is either you goofed up, like say you're trying to run two motors that are geared together in opposite directions, so they kind of start killing each other, and that'll cause a motor to burn out because of too much load. Or either build messed up, right? They may have chosen the inappropriate motor for a specific application, right? In the case of inrush current can be actually a very big problem for us, and we had a really big problem with that in our 2019 year. So what would happen is our drive base, because our drivers would be very aggressive with it and kind of go from 0 to 100 in over and over again, right? This caused a lot of wear on our motors and on our battery, causing frequent brownouts. And we'll talk about brownouts in a future video. And so the way we solve this is kind of allowing the motor to ramp up to from 0 to 100, not going instantly, but kind of applying a nice curve to it. And we achieve motor ramp up through something called PWM, which is pulse width modulation, which I'll talk about in the next video, which is about control. And through this motor ramp up, we kind of reduce the inrush current and keep it within safe parameters. All right, next thing to talk about is about inductive discharge, which is the thing I showed you with the drill, right? And the way we limit inductive discharge, motor controllers usually have a safety for this built into it. I won't really talk about how it works, but it's a series of diodes. If you don't know what a diode is, don't worry about it, right? That kind of limit the negative voltage produced by the inductor. And just something to keep in mind is when you run a motor without a motor controller, like say you're testing a prototype, right, over time the motor will wear out because of the large inductive discharge. Just be careful about that. Okay. And finally, I didn't really talk about this much, but we also have the internal resistance of the motor, which is that little resistor I showed you guys when I did the electrical breakdown. And this internal resistance kind of sucks away power that can be used in actual rotation and actual motion. And this internal resistance increases with temperature. And so if we want to reduce the internal resistance, we're going to reduce the temperature, we use cooling, right? And the cool thing, like with the Falcon 500s especially, is they come with a pneumatic port where you can pump air through the motor and cool the motor, right? So the hotter the motor, the less efficient it's going to be, so you're going to keep your motors nice and cool. All right, we're going to wrap up with one example problem. All right, our example problem is a motor has a supply voltage of 12 volts, an internal resistance of 0.27 ohms, and a current draw of 15 amps. What is the back EMF being supplied by the motor? I'm gonna give you a few seconds to pause. All right, so we're gonna use the equation I had in a few slides ago, which is that the current draw, or I sub m, is voltage supply minus voltage EMF all over the resistance of the motor. Okay, and so if you rearrange our equation to isolate voltage EMF, we get voltage EMF equals negative current draw times resistance of the motor plus voltage supply. Plug in the values we know, and we get that our voltage EMF is 7.95 volts. Okay, so that's it for this video. Our next video is going to be on control, and please let me know if you have any questions. I know this can be a little tricky, and so I hope you guys have a good day.